Okay, so in the last video, we started talking about solving single and double integrals by way of polar coordinates r and theta. And we kind of finished by saying, well, okay, I have, assuming my region is maybe circular in nature in the plane, then it makes sense to maybe convert from rectangular coordinates to polar coordinates and then integrate that way. And we actually looked at some examples where that was true. The kind of natural follow-up to that is, and where we finished last time, well, what if my region, instead of being two-dimensional, is three-dimensional? And I kind of have this circular, or I guess if I took a circular region and extended it upwards, it would be circular, but it would actually be more cylindrical, because I'd have a circle in the plane and I would be extending it this way. So what if the region I'm integrating over is more cylindrical in nature? Does it make sense to use polar coordinates to integrate that? Well, yes and no. The region is circular, so the polar stuff works, but the polar stuff is also two-dimensional in nature. We use it for single and double integrals. If my region is three-dimensional, cylindrical, then polar coordinates don't work, because my region is three-dimensional and polar only gives me two, r and theta. So what we do is we actually expand on that and we use what's called cylindrical coordinates. And essentially, all we really do is, instead of having r and theta, I add a third component, a third dimension, z, a height. And the good thing is, we have all these conversions. X equals r cosine theta, y equals r sine theta, x squared plus y squared is r squared, tan theta equals y over x. But now I need a way to convert my third component, but my third component in rectangular coordinates is z, the height, and the z here is still giving me the height, which just means I can just let z be z. So there's really no conversion at all. I do all the exact same conversions I did before, I just happen to have a third variable, third dimension z floating through the problem. The actual picture, if it helps, I have some point in space. So let's see, the first thing I do is I set up my point right here in terms of r. So now, if I do this, and diagonal, so it would look like that. This is clearly the x value, which we also write as r cosine theta. This is the y value, which is r sine theta. That's my radius r, but now I want to project this point vertically, so I'll just extend it up here so it's easy to see. And now, if I draw it at the same rough angle, there we go. Now, this is my height z right here. And now, this point is my point in space, which I can call xyz, or r theta z. And I guess if we need an angle, the theta angle is always from the xy axis, from the x-axis. So there's my theta right there. And again, we already have all these conversions in the plane for our polar conversions. Now I just add a third dimension z, which is identical to the same z I had before. But then the natural follow-up to that is the exact follow-up that I had before. I have a student coming, give me 1 second, making a video, but you're good, thanks. Okay. The natural, that was a student coming to my office. The natural follow-up to this is, well, when I do these in the plane, I had to come up with some type of rectangle. As it turned out, my rectangle kind of ended up looking like a sector of a circle. We called it a polar rectangle. It's a regular rectangular rectangle that was curvy because of the nature of the coordinates. Now the question becomes, if I have some three-dimensional region that is somewhat cylindrical in nature, and I know I want to use some type of cylindrical approach to approximating the volume of that region, what type of shape do I actually get? Similar to my polar rectangle here. And one way to kind of visualize this is to create coordinate planes from all of your coordinates right there. And here I'm not going to draw these out, they're pretty straightforward. If I fix Z, I just get horizontal planes. So that's kind of one component of my cylindrical rectangle, horizontal planes. If I fix theta, I just get an angle. I actually get, this one maybe is a little bit confusing. If I fix theta, this is X and this is Y. Maybe I fix theta right here. So we'll call that theta sub 1. Then I get this plane right here. Essentially a plane perpendicular to the XY plane. If I picked a different theta, I'll change colors. And maybe my new theta will have it go backwards just so it doesn't overlap. And that's my new theta. Then I get this plane right here. So different thetas give me different planes perpendicular to the XY plane. The Z planes are parallel to the XY plane. And then R, if I fix R, I get a fixed radius, which in the plane is just a circle. But then if I project it upwards, I get cylinders. So I essentially have cylinders of different radius. And ultimately, I use all three of those things to generate my polar rectangle. But we can draw this out, or I can attempt to. I will point out, people, the drawing I have in my notes is incredible. Now I'm going to try to recreate it here. So first, in the plane, I'm going to have two thetas. So that's theta 1 and theta 2 right here. And then I need two radii. So we will say that's my first radius and that's my second radius. And now we recall, this is essentially my polar rectangle from before in the plane. And when we did that, if this was R sub 1 and this was R sub 2, this was delta R. If this was theta sub 1 and that was theta sub 2, this distance was delta theta. And we picked a point right here to help me generate the area, which I called R cross. That's not a T. That's my bad attempt to draw a little cross like that. And it was just this point right in the center of that polar rectangle. But now I want to project this upwards. So there's that. And now, let's see, up to my ability to draw. There's part of my polar rectangle, but keep in mind my this is part of my cylindrical rectangle, but part of my rectangle requires a change in Z. I already have the change in R and the change in theta. I need a change in Z, which means, of course, I then have to project this upwards. And not great, but you all get the idea. There's my cylindrical rectangle there. Got to keep all the terminology straight. And right here, the change in height is my delta Z. Well, now we know how this works because we've done it at this point multiple times with rectangles in X and Y, rectangular prisms in X, Y, and Z, polar rectangles. I need to find the volume of that region. But this is clearly a prism. It's this shape projected upwards. by definition, the volume of a prism is the area of the base shape, which again in middle school I think they call it B, times the height. So now, my volume, area of the base shape, we already calculated it that last time using this R plus, which made it easier, and we got R cross delta R delta theta. But then you multiply by the height, but the height of this is just delta Z, which means my volume is R cross delta R, that's the area, R cross delta R delta theta times the height, which is delta Z. And now I have a nice formula for the volume of that cylindrical rectangle. My brain wants to keep saying polar rectangle. But once I have that, well, now I know how this is going to work. I have the basic formula for the volume of a cylindrical rectangle. So now, if the region that I'm integrating is the three-dimensional region that I'm integrating in R3 is cylindrical in nature, then how do I approximate the volume in that region? Well, I partition it using these cylindrical rectangles. And then I make that partition get better and better and better, and then that approximation for the volume gets better and better and better, and ultimately it becomes exact. If I take the limit as the magnitude of the partition approaches 0, it is all the exact same trick that we understand. But all that really means is, ultimately, if I want to find the full volume of an arbitrary cylindrical region, we'll just say delta V is equal to the summation, as I goes from 1 to n, of the function value, which again is that extra component that we multiply by, because while this region I'm getting the volume of this region, the actual function value is the four-dimensional thing, which I always multiply by. So we get f of Ri star, theta I star, Zi star, times my volume right here, which is R sub I cross, delta Ri, delta theta I, delta Zi. And then that will approximate the value of the function in that four-dimensional thing that's encapsulated by this region right here. Or in this case, I'm adding them all together, so this will approximate it reasonably well for me. But then how do I make that approximation better? Well, I take the limit as the magnitude of the partition approaches 0. And then that becomes exact. And then we know how this works. I have the limit of a Riemann sum, which means ultimately this becomes a triple integral over some region, which now we'll call f of R theta Z R. Just like we had this extra R floating around with our polar integrals, we'll have it here for cylindrical because we're doing the same conversions. dr, d theta, dz. And now I have a nice form for a triple cylindrical integral that I can solve. The only problem is the exact same problem that we had before. Well, how do I evaluate that? Ultimately, we understand how this works because, again, we've seen it repeatedly here. If this was a seated class based on past history, this lecture actually would not be too long and I'd be trying to fill time. And then this is one of the classes where I basically say, hey, spend an hour messing around with a bunch of these integrals. Because by now, the trick should be pretty clear. And we understand now if I'm going to convert from, say, a rectangular to a cylindrical integral, I'm going to have to do some conversions, but we already did those for polar ones, so we understand how it works. The only new thing is the z, but that actually doesn't get converted at all. That stays the same, which means these are actually pretty straightforward. And the only way you really learn how to do them is by messing around with them. All that to say, this lecture video isn't going to be much longer. We're going to go through maybe one example. I might have a second one. I'm not sure. I'll think about it. But the only question, like I said, was how do I integrate this particular integral over the region F? And we actually do exactly what we did before. And here, rather than trying to look at different regions and say, well, if it looks like this, then we'll say it's rectangular, so we'll do it one way. If it looks slightly different, then it's non-rectangular, so then it's a general region. So then if it's a general region, we'll do this, because Fubini has a theorem for everything. Now we're just going to use a general region. And we understand whatever my general region looks like, I just have to figure out if it's, well, let's see, before we had type 1 and type 2, then we had x, y, and z simple. Now I have r, theta, and z simple, but the principle is the exact same. So we're just going to generalize how to solve this out. And this is just equal to the triple integral of f of r, theta, z, r, and in my notes, just to keep all my lettering the same, dz, dr, d theta, where theta goes from theta 1 to theta 2, r goes from, which letters did I use? G of theta to h of theta, and z goes from g of r theta to h of r theta. I integrate with respect to z first, so z has to be a function of the other two variables, r and theta. Then I integrate with respect to r has to be a function of the other variable, which is just theta, and then the outside limits, theta, have to be constants. But keep in mind here, this is a general region, we've seen this before, mostly because I don't want to have to come up with lots of different cases here. But quite often, those thetas will be constants if they're on the outside. But say these functions of theta, h of theta and g of theta, my limits on r, those will also be constants. In theory, these could also be constants here, and we get a nice simple iterated integral to solve. We're just generalizing this because we understand how the trick works. Given a region in R3, if I feel like doing it, convert it to cylindrical coordinates. Once I convert it to cylindrical, see if it is z simple, r simple, theta simple. Figure out my limits by writing out my region F, which will tell me my limits. Then just plug in and integrate. So, as an example, define the region bounded by z equals 8 minus x squared minus y squared, and z equals x squared plus y squared. Then find its volume. So the first thing we do is always to sketch out my region. And at this point, all of you are good with your quadric surfaces. This is an upside down parabola whose maximum is 8. And it's going to go downwards. And I'm going to deliberately hold off on drawing it right now. We'll see why in a second. This is a regular paraboloid, I said parabola, going upwards. And essentially, this one is going to go up, and then this one is going to come down, and hopefully they'll intersect somewhere nice in the middle. Not always a guarantee, but we're going to kind of hope for that here, because it's set up the problem that way. And I want to find the volume of that. Couple of things I will point out, it's not a sphere. I mean, you can easily see it's not a sphere. This just looks like a sphere because of the way I drew it. But these are different sizes, so it's not spherical. I would also point out, if this intersects in a nice place, well then if I drop down into the XY plane, I should get a nice circle in the XY plane, which is a nice region there. I suppose if we're going to do that, we should at least check. If I want to know where they intersect, I set them equal to each other. So I get 8 minus x squared minus y squared equals x squared plus y squared. Add those, I get 2x squared plus 2y squared equals 8. Divide everything by 2. I get x squared plus y squared equals 4, which means they intersect on the circle centered at the origin of radius 2. So that's where these two things intersect. And then the question would become, I want to find its volume. So I understand I'm going to do a triple integral and integrate the function 1 to get the volume in 3 dimensions. And could I do this in rectangular coordinates? I could certainly try it, yes. It's clearly z-simple. I come up through here and I always enter through the greenish one and exit through the blue one. So it's clearly z-simple. Once I know it's z-simple, I know my inner limits. Then I can drop down into the plane, which is a circle, and then I know I can integrate the circle. I may have a problem, as we've seen before, because you end up with these either an x squared or a y squared inside a square root, and that might cause a problem when integrating, although if this is just the limits, maybe you're okay. So we understand, because we've done it before, once you have squares and you ultimately have square roots floating around, occasionally that can make your integration more challenging. So we could do it that way, and I would actually encourage you, because I have said this before and I do reiterate it, on exams, I'm going to make you do that. Hey, here's an integral. Solve it with rectangular. Solve it with cylindrical. Now, I don't necessarily say I would tell you which way is better. Maybe I would say set it up with rectangular, set it up with cylindrical, and then pick the one you're going to solve that you think is easier. And I do stress this, you all know me, I will deliberately give you ones that can be solved in multiple ways, but one way will always be easier. So essentially, say you're doing an exam, do it one way, solve it in 5 minutes, do it another way, solve it in 5 hours, and that's not an exaggeration. So again, we've established the understanding of the different types of integrals and the different ways to set them up is what we're going for, because all of you can integrate. We want you to understand the problem so you can set it up and pick the best way to solve it. Here, just because we're talking about cylindrical things, and clearly this is cylindrical in nature, we're going to go with cylindrical coordinates. So first off, I have to rewrite these in cylindrical, but I know that x squared plus y squared equals r squared. So this just becomes 8 minus r squared, and that's my top. This becomes r squared, and that's the bottom. There is no e at the end of bottom. And this right here, they intersect, as we said, at the circle of radius 2, which in cylindrical and even in polar is just r equals 2. And if nothing else, we know my limits here will involve square roots and things like that, which can be messy. Here, my limits on r are going to be nice constants. It's just r equals 2. So right away, I see the cylindrical may actually work better for me. All the x's and y's disappear, and I just get one variable. So now I just need to set it up. The first thing we always do is set up my region F. And let's see, r, theta, z. My r, clearly I start in the center and go outwards to a radius of 2. So 0 is less than or equal to r is less than or equal to 2. Theta, in the xy plane, I'm getting a whole circle. So my theta just ranges from 0 to 2 pi. And I would actually stress here, this theta is the angle in the plane, which means it has to be between 0 and 2 pi. you can't go beyond 2 pi because you'll be overlapping yourself. And while not true in general, a lot of the things we do, because they're cylindrical in nature, and that's when we use cylindrical coordinates, a lot of times theta will go 0 to 2 pi because we'll be spinning all the way around the axis. It's not always true, but in many instances it will be. Now I need z, but we just said that's the bottom and that's the top. So r squared is less than or equal to z is less than or equal to 8 minus r squared. There's my region F. So now I can write out my triple integral. And it's the function 1. You don't have to write that. I always do it just so we're clear. R dz dr d theta. And then my limits of integration, theta's on the outside, that's 0 to 2 pi. R is next, that's 0 to 2. Z is first, that's r squared to 8 minus r squared. And again, here I stress when we had the general form of the integral, this was a function on the inside, but we see here it turns out to be a constant. This was a function of r and theta, and again, technically it is, but the thetas actually aren't involved in the equation right here. So do not assume your limits have to look a certain way. A lot of times it can be constants, it's not a big deal. Now just solve this. And I am not going to take the time to solve this out, because all of you can do it, but to actually get the solution, it is 16 pi. Which, if nothing else, tells you this has to work out really nicely, because that's a nice simple answer. So the integration should work really nicely. A few of you did either email me or stop by the collaborate sessions in the last few days and ask questions about some of the integrals and solving them out. And for the most part, the integration was always correct, beyond maybe missing a trig integral, like a sine, cosine type thing, and differentiating, not integrating, or randomly missing a negative sign. Which again is good, because if nothing else, it means we understand the trick at this point. We understand how to set up integrals and find limits, and then it's just cleaning up the actual integration itself, which is only going to come about by way of doing a bunch of integrals, which is, like I said, what in class, this has been about a half an hour, I think, if I can see those numbers. Yeah, I think it's about a half an hour. In class, this would be one of the days where I said, good, we have an hour left. Do 10 problems in your book. Start with rectangular, convert to polar, or start with rectangular, convert to cylindrical. Set up all the limits, solve problems both ways, and then see if you can determine which way is easier and better for you. And as it turns out, well, sometimes this isn't the best way to go, and sometimes rectangular isn't the best way to go either. And then we need to come up with another way to do our integrals. And I'm going to save that for Monday or Tuesday night when I make the video. I do stress though, we did all of the differentiation stuff and had an exam. Now we've done all the integration stuff, both all the stuff from the last chapter on integration, chapter 4, on double integrals and triple integrals with rectangular coordinates, as well as applications. Here we're not really calling it an application, but we're actually taking the volume, which we called an application last chapter. Again, now in chapter 5, we're doing cylindrical integrals. We did polar integrals. We have one more type of integral to look at, and then we're going to have another exam covering all the integration stuff. And we understand, again, while we don't necessarily say, now we're going to do some applications, we already understand the applications, so we just throw them into the problems. Ultimately, you now have a whole lot of tricks. As a guy I knew in grad school used to say, you have a whole lot of tools in your mathematical toolbox. Now I just give you a whole bunch of problems and say, figure them out. And that is what we would do if this was seated. So that's what you get to do over the weekend with all the homework I posted. And then, like I said, next week we'll look at the last set of integrals, the last type of integrals, and then we'll go from there.